Bad movie physics. Our first clip comes from an Indian movie called Bahubali 2. In this clip, we see 6 armored men being launched off a tree catapult and landing on the other side of a fortress. Physics would not allow this to be plausible, as the distance the group of men traveled in the movie is 80 meters. We researched this value and found it, and the vertical distance they would reach is 60 meters. So we use the equation 1/2 v times t equals 60 meters to calculate the vertical component of the velocity. Firstly, to find the velocity variable, we use the equation acceleration equals the rate of velocity with respect to time. Plugging in gravity for acceleration, we can find v to equal 10 times the time. Plugging this into the other equation, we get 10t squared equals 120, with the final value of time being 3.46 seconds. So this would result in the vertical component of velocity to be 34.64 meters per second. And then using the time, we can find the horizontal component of velocity with the equation velocity equals distance over time, with distance being 80 meters. The horizontal component of velocity is 23.09 meters per second. Using the Pythagorean theorem, we can find the diagonal velocity at which the men are launched to be 41.6 meters per second. Using a protractor, we approximated the angle when they are launched to be 55 degrees, and the average height of a palm tree is 18 meters, so we will use that for the initial height. Plugging in all these values into the range equation allows us to calculate the distance they would travel to be 174.4 meters. As you can see, this is much greater than the actual distance the men traveled in the movie, or allegedly traveled, being 80 meters. So in reality, the 6 men would travel 174.4 meters.
Our next clip comes from The Flash.
There's fire everywhere! Cisco, are you still there?
Mom? Mommy?
Everybody's out.
In this clip of The Flash travels into a building and saves a girl that's standing in a burning hallway. The Flash travels about 150 meters horizontally into the building, and he takes approximately 1 second to bring the girl out of the building. So that this means that his velocity is about 150 meters per second. Using this value, we can also calculate the acceleration when he's dropping the girl outside, using one of our kinematic equations. This means his acceleration is approximately 75 meters per second squared while he is decelerating. These calculations mean that the girl that he's attempting to save goes from standing completely still at rest to a speed of 150 meters per second in a matter of only 1 second. This means that her neck would most likely be snapped and her brain would hit the back of her skull with such intensity that she would eventually either have a concussion or her brain would swell up and bleed, eventually killing her. The Flash also saves the girl, then goes and drops her off. Because the Flash is only holding her at one point on her body when he goes from 150 meters per second to completely standing still, this means that her entire body around that point will want to continue moving in the same direction due to inertia. Kind of like how the water on these cherries continues moving in the same direction even after the cherries have touched. This means that her spine will have snapped and her neck would have also broken, causing her to die.
Our third movie clip is from Wonder Woman. We will be looking at Wonder Woman's bracelets of submission. A German soldier shoots our heroine. The bullet hits her bracelets and ricochets at the same speed, but in the opposite direction. To do this, I must determine the mass and speed of a bullet with an approximate mass of 4.2 grams with a speed of 965 meters per second. With that, I can find the change in momentum in one dimension. The bullet initially moving in the negative direction with a negative velocity. When I find the difference, the negative of a negative is a positive, and the change in momentum is twice the initial momentum. Inserting the values for the mass and speed, I get a momentum change of 8.1 kilogram meters per second. Now, if the bullet experiences a change in momentum, Wonder Woman must experience the same change. Assuming she starts from rest, final momentum would be 8.1 kilogram meters per second in the negative direction, using a mass of 50 kilograms, which is an approximation. Wonder Woman would have a recoil velocity of 0.162 meters per second or 0.36 miles per hour. That's super slow, and that's if she's on ice, which she isn't. So a single bullet striking a bracelet of submission would do very little to push Wonder Woman backwards, and nothing would happen if you're on normal ground. Okay, so one bullet fired from a rifle might not be such a big deal, but what about a barrage of bullets from a machine gun? For simplicity, I will assume this German submachine gun fires at the same rate of bullets at the same speed as a rifle, just at a higher rate. I think an estimate of 500 rounds per minute, or one round every 0.12 seconds, is a good figure for a World War I era weapon. Knowing the interval between bullets, I can do more than simply find the recoil speed of Wonder Woman. I can determine the average force the bullets exert on her as they hit her, bracelets of submission. To do this, I will use the momentum principle in one dimension. This states that the net force on an object is equal to the rate that the momentum changes. I already have an expression for the change in momentum of a bullet from the rifle example. If I use the time interval of 0.12 seconds, I get an average force of 67.5 newtons. This is about what you'd experience with a small dog sitting on you. No big deal. With just a little bit of friction, Wonder Woman could easily withstand the impact of several submachine guns unless she was standing on ice. So what kind of reaction time would Wonder Woman need to block a bullet with her bracelets? So here's the situation. Some bad guy fires at her with the bullet moving at 700 meters per second. Although the value is different than earlier, I want to use a more reasonable. Wonder Woman's reaction time depends not only on the speed of the bullet, but the distance she travels before hitting her. Let's say the bad guy is 30 meters away from her. If the bullet travels at a constant speed, I can use the definition of average velocity to find the travel time. Inserting my values for speed and distance, I get a bullet travel time of 0.043 seconds. All of which is to say, Wonder Woman is superhuman, and you should definitely not try blocking bullets, even with the bracelets of submission.
Our final clip comes from a movie in the Avengers saga.
You didn't see that coming?
In this movie, we can see a person running around faster than any normal human could imagine. This character is Quicksilver. We can take his estimated weight, which is 140 kilograms, and his estimated acceleration that we found online, which is about 50 meters per second squared. Using these values, we can find that he runs about 5 meters in only 0.1 seconds. We can plug these values into the force equation F equals ma, with 140 kilograms and 50 meters per second squared as the mass and acceleration, to find that he applies 7,000 newtons of force downward on his legs. The normal human leg, after searching online, can only take 4,000 newtons of force until it breaks. This means that instead of zipping around, Quicksilver would actually be breaking his legs while running around so fast.